So our next speaker is Feng, who is from Beijing, Xiaotong, and he's going to be telling us about instructions for optimal Ferrers diagram rank metric codes.
Thank you. First, I would like to give my thanks to all the local managers in Singapore. Thank you for your making an excellent organization for this excellent conference. My talk is on some constructions on Ferrers diagram rank metric codes. This work follows Chui's work too much, so thank you, Chui. Okay. This is joint work with a PhD, Shangxin Liu, and Professor Yan-Xu Chang. First, I will give some definitions on this problem. Let FQ M times N denote the set of all M by N matrices over FQ. It is an FQ vector space. For any two matrices A, B belonging to FQ M times N, we can define their rank distance by the rank of their differences. M by N K delta Q rank metric code C is a K-dimension FQ linear spaces of FQ to M by N with minimum rank distance delta. What's Ferrers diagram rank metric code? It's a special kind of rank metric codes. A Ferrers diagram F. A Ferrers diagram F is a pattern of dots such that all dots are shifted to the right of the diagram, and the number of dots in a row is less than or equal to the number of dots in the row above. Here is an example. This is a 5 times 4 Ferrers diagram, and we can count the number of dots in its columns. In the first column, there are 2 dots. The second column, 3 dots. So we often use this notation to represent such kind of diagram. Ferrers diagram code C is an M by N K delta Q rank metric code such that all entries not in the Ferrers diagram F are 0. So this place, when we fill, they are all 0. We often denote Ferrers diagram code by such kind of parameters. Of course, in this case, we often refer it is linear. In this talk, when we say a code, such kind of code, we all means a linear code. Just now, Julie has introduced many background on some of this code. Actually, Ferrers diagram rank metric code was introduced by Julie and Silverstone in 2009. They presented a very excellent and simple construction. It's very effective to construct subspace codes. Their method can produce a good subspace code. Good means the code can achieve are close to the theoretical upper bound. Yes. And in their paper, they found this kind of code are very important. So here, when I prepared the talk, I intended to introduce some ideas of Chubi, but because of time, so I think it's better for me to skip this part. If I have time, I will recall your work. Okay, we're going to the central part of this construction of our topic. I want to see something construction. First, we need to review what's the upper bound on the side of FDRM codes. Let delta be a positive integer, and let f be a Ferrers diagram, and let cf be its corresponding code. Then the dimension k is smaller and equal to the minimum value of vi. I read from 0 and to delta. And here vi means the number of dots in f, which are not contained in the first rows and the rightmost delta -1 - I columns. if an FPRM code which contains this upper bound that is called optimal. Okay, here we give an example to illustrate the definition of VI. Here this is a 2x2 Ferrers diagram. So according to the definition of VI, here the delta equals 2, so I equals to 0 or equals to 1. So V0 is the number of dots which are not contained in the first in the 0 row and the rightmost one column. So 2 dots are left. Similarly, when I equals to 1, we remove the first row 2 dots. Then the 2 dots are left. So the upper bound of the dimension is 2. So from theoretical, the upper bound is 2. We need to find an example to achieve it. For this example, it is easy because all the codes we considered in this talk are linear. So when we check the rank of any 2 different codes, we just to check the rank of any code order. Okay. So you can check these 2 codes at least rank 2. Okay. This is definition. And of course, the next question is whether the upper bound is tight. There's a conjecture. The conjecture is that for every Ferrers diagram and every finite field, the conjecture should be tight. And here's a remark. The upper bound still holds for FPRM code defined on any field, not just focus on the finite field, because of the application is in the communication. So generally in the application, we just focus on the finite field FQ, but if we relax the condition on any field, there's a counterexample. Dollar and Yamagnani show that for algebraically closed field, the bound sometimes cannot be achieved. So far, all the known results on the code defined on finite field are tight. So I mean, the conjecture so far are all correct. Okay. I mentioned some known results. When delta equals to 1 or delta equals to 2, for any Ferrers diagram, the conjecture always correct. When delta equals to 3, for the square Ferrers diagram, the conjecture is true, but for the rectangle square, the conjecture is unknown here. Okay. When delta is greater and equal to 4, the conjecture is also unknown. When the Ferrers diagram is a full Ferrers diagram, full means if a Ferrers diagram is of size m times n and consists of mn dots, okay, meaning it's full. In this case, the upper bound is coincides with the singleton-like upper bound for MRD code. Okay, any rank metric codes, m times n k delta q code always satisfy this upper bound. This is a classical upper bound. Okay, it is easy to count this bound for okay, when I equal to 0, when I equal to 0, according to the definition, V0 is the number of dots which are not contained in the 0 rows and the rightmost direct -1 columns. So you can have this bound. Okay, it's the same. When the quality holds, C is called a linear maximum rank metric code denoted by this notation. It is known that linear MRD codes exist for all feasible parameters. Okay, these are the known results. In this talk, I want to see some constructions. Here, I will mention 5 constructions. The first one is based on the use of maximum distance separable code, briefly MDS code. MDS code is a code with this parameter. It is a linear Hamming code with dimension k and minimum Hamming distance d. It is known that this code always exists for q greater than or equal to n minus 1. These constructions was first given by Ethan and his other colleagues. Okay. I will illustrate their idea by this example. Okay. Here for this example, first we want to construct a Ferrers diagram with this parameter. Here we hope the rank distance data at least equal to 3. How do it? Okay. First, we labeled these 4 diagonals by D0, D1, D2, D3. This is the 4 diagonals. We can first put an MDS code on D3 with these parameters. Here 4 means the length of the code. So here there's 4 dots here. So the length is 4. And 2 means the dimension, 3 means the minimum handling distance. So in each non-zero code word of this code, there are at least 3 non-zero coordinates. So in this case, we know the matrix of the rank could be at least 3. If all the 4 dots are filled zeros, then we fill 313Q MDS code on D2. Because of the parameters here, data equals to 3. So if all the 3 dots are not 0, then you can see the matrix at least the matrix rank are at least 3. So that's the basic idea to construct optimal F33Q code. Okay. Here dimension 3 is this dimension 2 and dimension 1 plus. Okay, it's 3. We generalize this construction slightly. The basic idea is we want to, because we know this type is very special, it is of some diagonals, so we want to replace each dot by another Ferrers diagram. We make another example. Okay. Okay. First, we start from this Ferrers diagram. It is of some diagonals, so we can construct an optimal F25 field code by our MDS code, the similar method. Okay, we can fill D5 and D4 with 515 MDS code. Okay. And then we can have this parameter. And now we want to replace each dot by F1, this Ferrers diagram. So, I mean, finally we want to obtain this Ferrers diagram. And let A1, A2 be a basis of C. Be a basis of C. And for F1, we can construct an optimal F132 field code. This is an MRT code. It has dimension 3, so that B1, B2, B3 be basis of it. So this is rank dimension 2. This is dimension 3, and we can give this result. Then there is an optimal F prime 610 field code, and here it's a Kronecker product AS Kronecker product BL. So this is dimension 6. Okay, and the rank distance is here. This rank distance is 5. This is 2, and this is 5 times 2, so it is 10. Okay, this is the basic idea. Of course, we can try to replace each dot by a different Ferrers diagram, not the same one. So a slightly generalized example, we need a generalized Kronecker product. Let A belonging to FQ M times N at B1, B2, Bn be a by block matrix where each BL has the same number of rows. Okay. A generalized product B1, B2, Bn is defined by this one. Okay. One B1, B2, Bn are equal. It is just the classical Kronecker product. Okay. So we write our construction that F be an M times N Ferrers diagram and Fi be an S times Ti here. Each Fi has the same number of rows, and if there exists an Fp1.1 code. Here we require the master code must be constructed via MDS code. Then you can have this construction. Of course, a natural problem is whether we can delete this construction or give out another conditions. Okay, reject this theory. So far, I don't know. Okay. The third construction is to construct a new Ferrers diagram from O. Okay. We want to construct a code with Ferrers diagram F. If F can be partitioned 3 parts, F1, F2, and D hat. If there exists an F1, K1, delta 1 code, if there exists an F2, K1, delta 2 code, and if there exists an D, K2, delta code, and you can find this this parameter. Okay, you can find a code with this parameter. Here D hat means, because here D is a Ferrers diagram, so Ferrers diagram has the shape of some diagonals. So D hat is obtained by adding the fewest number of new dots to the lower left corner of D, so that is a Ferrers diagram. This construction generalized to its constructions in 2006. In their paper, they require D is a full Ferrers diagram, full diagram. Here we relax their condition. This construction has this disadvantage. If we want to obtain an optimal code, we require F1 part is optimal, F2 part is optimal, and D hat part is optimal. But if the optimality of the D hat part is unknown, then what shall we do? So we give we give another idea. Okay, we illustrate by example. Okay, here we denote the blue part F1, green part F3, and the black and the yellow part is the D hat part. Okay, because so far, according to all the known constructions, the black plus the yellow part, the code's optimality is unknown. So then the bio construction will be unused to obtain an optimal one. So the idea is we want to remove the yellow one, and we mix the yellow one to the blue one. So I mean, we form a new Ferrers diagram named F12, and because now only black one left, black one is F4. This Ferrers diagram, you can construct an optimal one. Since the above procedure from F to F star use a natural bisection, so we can from F star to form an F. Okay. Of course, we can check the rank distance, but I need the details. I just mentioned the idea is to mix. Okay. If we'll, okay, mix. Here in this example, the concept proper combination of F1, F2 is important. Okay, so here's the definition. What's the mix? Okay. This definition is a little complicated. Here, the key part is condition 3. In language, condition 3 means that if 2 dots in F1 and F2 are in the same row or same column, then their corresponding 2 dots in F are also in the same row and same column. I mean, they can mix, but they must satisfy the condition 3. Okay. And okay, we write it in theory is like this. Here we want to mix this part F2 to F1. Okay. I mix the details. Okay, this is the construction. This construction has a disadvantage. That is, you can see the resulting code has dimension k equals to the minimum value of k1 and k3. So that means we lose some dimension because we take the minimum. So we want to improve the resulting code's dimension. So a natural idea is we can make a further combination. We combination not F1 and F2. We combination F1, F2, and F3. This can improve the resulting code's dimension. So we give another construction, we name construction C. This construction has disadvantage. The disadvantage is even though the dimension is improved, but the rank is reduced. So, okay. The fourth construction is this one. Okay. That beta equals beta 0, beta 1, beta m1, m minus 1 being an ordered basis of FQM to FQ. So for any element in FQM, it can be represented according to this basis. Okay. So based on this basic idea, Cao Zhang and Zheng Niange give the following theory. If there exists an FK dot QM code, here f equal to this parameter. This parameter gamma j means the number of this Ferrers diagram. The jth column has gamma j dots. Okay. Then the idea is replace each dot by a column, by an m times 1 column. In the original code, each element is from FQM. Because of the above representation, it can be represented each element in FQ. And in this case, the column expands. Okay. Another idea is maybe we can use another representation of elements in finite field. So we use another representation. Let Gx equal to this one be a primitive polynomial of FQ whose continuous matrix is G. By the Cayley-Hamilton theorem, engineer algebra G is the root of Gx. Then this set equipped with the matrix addition and matrix multiplication is isomorphic to FQM. So that means each element can be each element in FQM can be represented by an m by m matrix. So each dot can be replaced by an m by m matrix. That's the basic idea. So we write it in the following form and omit the details. And in some cases, we can obtain optimal codes. The final construction is based on subcode of MDS codes. Okay. Because of time, I omit the detail. I just mentioned our main results. So I mean how to do it. I just mention our results. Okay. I mentioned another one. Okay. We can obtain this result. Okay. In this theorem, there is a parameter r. When r equals 1, we can obtain two results. Actually, the technique is similar, but we just prove it more carefully, and we generalize the results. Actually, you can compare it with the original theorem. It says that if each of the rightmost dot minus 1 column of f has at least n dots, here we relax this dot minus 1 to dot minus 1 to n minus r. And another main result is this one. Okay. When omega equals 1, Zhang and Ge obtained the same result. So here we generalize that result. In language, it means the first k columns we required it contain at least T2 dots. In their paper, they required each of the first k column contains at least T1. T1 is smaller than T2, so we generalize the results a little. Yeah. So, okay. So I have, my time is over. Yeah. Thank you.
Okay, in the interest of time, we might leave questions till the tea break. So we're back here at 3:15. Let's thank Tao again.